So the next thing we have to talk about is the velocity of blood flow. The blood flows quickly in some places in the circulation, and we want it to slow down in other places. It's very much akin to a ski lift. You want the ski lift to go slow where you get on and off, and you want it to go fast as you're transiting the hill. We want blood to be going slow through the lungs where oxygen is getting on and carbon dioxide is getting off. We want it to go fast out to the periphery, to the capillary beds in the periphery, where we want it to slow down again. So we can regulate the speed, the velocity of the flow, based on the total cross-sectional area. When you're whitewater rafting, you know that a rapids, where the water is flowing quickly, is where the river is shallow and or narrow, or usually it's both. And the water goes very quickly through that section, through that gorge or whatever. When it comes out and it's wider and deeper, it flows more sluggishly. There's the same volume of water, but it's moving much more slowly. So you would think that it would be fastest in the capillaries, which are small, and slowest in the aorta, which is big. However, there's only one aorta, and there are millions of capillaries. So actually, the total cross-sectional area of the capillaries is way bigger than the total cross-sectional area of the one aorta. So it's actually the fastest in the aorta and the slowest in the capillaries, because you have to look at them all together. The same thing happens in the rad of your car. There's one hose that goes to the rad, and there's hundreds of tubes in the rad that the coolant distributes down, and then there's one hose that goes back to the engine of the car. So the coolant, pushed by the water pump, goes very quickly through the hose into the rad, where it slows down, is cooled off, and then it speeds back up with the cool water going back to the engine. It's the exact same thing. So so it goes slowest in the capillaries because that's where things get on and off. This is the total cross-sectional area. You'll see that it's on the order of 4,500 or 5,000 times the cross-sectional area in the capillaries as is in the aorta. It's a very, very large difference. So blood flows fastest in the aorta because that's the narrowest part, slowest in the capillaries, and then speeds up coming back through the veins in the vena cava. So how do we determine what tissue gets perfused and to what extent? So it's really autoregulation. That means the tissues themselves adjust the blood flow based on its requirements. And so it's really controlled by modifying the diameter of the arterioles that go into those capillaries. And so there are local things that drive that. And the local things are, there's two types. One is a metabolic and the other one is a myogenic determination. Now, the metabolic controls really are about vasodilation and vasoconstriction in response to things that are in the metabolically active tissue. So when the tissue O2 levels go down, that means that you've been using that tissue, you've been making a lot of ATP, and so that means it needs more oxygen. And that will cause vasodilation of those arterioles, and open the precapillary sphincters so that more blood goes through those capillary beds. Other things like acidity, the amount of potassium, adenosine, which is the A of ATP, inflammation, prostaglandins, histamine, those sorts of things all cause vasodilation and means that more blood flow in the area, and the blood will flow slower in those areas because of that dilation. So what happens is all these things cause the relaxation of the smooth muscle, and the endothelial cells make something called nitrous oxide, and it's released right there and causes vasodilation. Nitrous oxide is a vasodilator. Vasoconstriction is sympathetic control. It's the sympathetic nervous system that does that. The myogenic controls really are a mechanical reaction to to what's going on. So one of the things that happens in smooth muscle is this. When a smooth muscle is stretched, especially suddenly, then what happens, it's called the stress relaxation response. What happens is that it contracts in response to being stretched. Then it adapts to the new stretch and it stops forming a contraction. So what happens is if blood pressure goes up suddenly, then the stretching of the arterioles, because of that increased blood pressure, causes the muscular walls of that arteriole to contract, causing vasoconstriction, to actually lower the pressure there. And what it does is it smooths out the bumps. So that passive stretch causes vasoconstriction. A reduced stretch means that those muscles relax and it causes vasodilation. So what happens is you get the right amount of perfusion based on the pressures that are driving the blood to that tissue. Here's a kind of a list of things. Please do not memorize this. Just understand the difference between metabolic controls and the myogenic controls. And literally, when you look at it, the myogenic control is really just stretch. So those are the intrinsic, the autoregulation. The extrinsic are sympathetic neural stimulation and the hormones, which we've already discussed. Long-term autoregulation, so that's on the short term. The long term really is making new blood vessels. So when you can't meet the requirements of the tissue, then what you do is you just make new blood vessels so that you can meet the requirements. It happens in a small way anytime there is a hypoxic event. If somebody is climbing Mount Everest, they stop and acclimatize on the way up and for a couple of days, and they really grow new blood vessels to deliver oxygen more efficiently because of the lack of oxygen. It happens when you start exercising. Like if you have been a couch potato for a while and you go to the gym and all of a sudden your tissues are demanding more oxygen than they used to, then your arteries can't supply it quickly enough and you fatigue quickly. You fall out of aerobic respiration and into an anaerobic state because you can't supply the oxygen. So what your body does in response to that is actually grows new blood vessels, and that's part of the process of getting in shape. And now you deliver more blood to those tissues that you have been using. Now it's interesting because it happens in the tissues that are being used. So if you're doing the Stairmaster, you will have angiogenesis in your gluteal muscles. You won't necessarily have it in your back muscles or your arm muscles. If you're bench pressing, then you will grow it in the muscles that you're using for bench pressing, and not necessarily in your leg muscles, and so on. It makes sense. So in the skeletal muscles, and this is what really is important, because these are the real hogs of blood flow during exercise. So at rest, really it's the myogenic. So spikes in blood pressure and changes really are dealt with on a second-to-second basis. When you start to use the muscles, the blood flow increases directly proportional to the metabolic activity. So the more you exercise that muscle, the more we get blood flow. And the local controls start to override. And you can get a lot more blood flow to those. Blood flow to the brain is constant. So it really is both metabolic and myogenic controls. We use the myogenic controls mostly as safeguards. We use it so that the blood vessels don't rupture, so that the changes in blood pressure really don't affect the brain in a physical way. We use the metabolic controls during times of increased carbon dioxide, increased acidity, so which is a decline in pH, things like that. Maybe if it's bad enough, decreased O2. So the brain just doesn't do well with changes. Skin is very variable. It is, a lot of it is about maintaining body temperature. We bring more blood to the skin to radiate heat, to get rid of excess heat, because it's the surface area, and we stop bringing it to the skin if we're cold. We don't, so that we don't lose heat. That's a lot of that is neurologically controlled. We also auto-regulate for the oxygen needs, right? And the blood really provides the blood reservoir. When we need more muscle blood flow, we steal it from the skin. So there are a lot of capillaries in the skin, and we can shut them all down if we need blood someplace else. That's why if somebody's hemorrhaging, they go cold and clammy, because we divert blood away from the skin to the more vital organs, the organs that are more metabolically active and are needing it to make ATP. So I talked about temperature regulation already. You know, and when we start talking about sweating and that kind of thing, it's all part of it. Blood flow to the lungs is a special thing. The blood pressure in the pulmonary arteries is 24/8, not 120/80, so it's about 10 times less. Well, maybe not quite 10 times, but 5 to 10 times less. So the arteries and arterioles have large lumens, they're thin-walled, and because the circuit is really short. The autoregulation works exactly the opposite, which makes sense, because low O2 levels cause vasoconstriction, because you want to speed up the flow of blood through the lungs so that we can pick up more oxygen. So all the autoregulatory mechanisms work exactly the opposite, because the arteries have the opposite type of blood to systemic circulation. Blood flow to the heart is important. I mean, this is what causes heart attacks. So during systole, the coronary vessels are compressed, and that's why the heart has so much myoglobin. When you're exercising and the heart is needing to really contract rapidly and heavily to provide enough blood pressure, to provide enough flow, the coronary vessels dilate to slows through the capillaries to allow the loading and unloading. The sphincters, the precapillary sphincters, regulate the amount of blood in each capillary bed minute to minute to reflect the tissue's needs. Oxygen and nutrients go from the blood to the tissues. Carbon dioxide and waste go in from the tissues into the blood. If the stuff is lipid soluble, so if it's hydrophobic, it goes right through the membranes. If it's water soluble, it has to pass through spaces. The fluid movement through blood vessels is very, very important. We call this bulk flow. And really, there's two opposing forces in bulk flow. One is hydrostatic pressure, which is really the blood pressure. It's the force that is forcing liquid out of the blood into the tissue. And the opposing force is osmotic pressure, that it's because of the proteins and the stuff that's colloidally suspended in the blood that is causing an osmosis that is drawing liquid from the interstitial fluid back into the into the blood vessel. So the hydrostatic pressure really is in the capillary is the blood pressure in the capillary. It forces fluid out of the capillary walls. At the arterial end, where the blood pressure is 35, it's high. At the venual end, where the blood pressure is now dropped to 17, it is relatively lower. Now, there is a hydrostatic pressure of the interstitial fluid, and really that's caused by massage or wearing like support hose, or anything that compresses the interstitial space will actually cause that interstitial fluid hydrostatic pressure to go up. In normal tissue, the hydrostatic pressure is 0. The interstitial hydrostatic pressure is 0. The osmotic pressure from the capillary side is really caused by albumin. That's the main thing, so the non-diffusible plasma proteins. It averages about 26 millimeters of mercury. Now, there is materials found, proteins and things found out in the interstitial fluid, but there's not very much. So the osmotic pressure drawing liquid out into the interstitial fluid is very low. It's about 1, if that. So what we end up with are these net flows. We call this net filtration pressure. And really, it's all the forces acting on the capillary bed. So the net filtration pressure is the hydrostatic pressure of the capillaries, which is at the arterial end, 35, minus the hydrostatic pressure of the interstitial fluid, which for all intents and purposes should be 0, unless you're wearing compression stockings. So that hydrostatic pressure, which is the force pushing out, minus the osmotic pressures, which will net pull the liquid in. So that's the osmotic pressure of the capillaries due to the albumin, minus the osmotic pressure of the of the interstitial fluid. So it's about 25 minus 1, or 26 minus 1, so it's about 25. At the artery end, where the arteriole is, the hydrostatic forces are bigger than the osmotic forces. So it's about 35 versus about 25. So the net filtration pressure at the arterial end is about 10. At the venous end, however, the blood pressure has dropped, so the hydrostatic pressures have gone down to about 17. The osmotic pressures are about 26, so it's about 9. The net filtration pressure is about 9 going in. The difference between the 10 pushing out and the 9 going in is where lymphatic fluid comes in, and we'll talk about that in the next chapter. So this is a picture of it. It's the hydrostatic pressure is 35, the osmotic pressure is 25, so it's about 10 out. At this end, it's about 17, 25, 26. It's about 8 or 9 in. A lot of different things can change this. For instance, if you have liver disease and you don't make albumin, the net osmotic pressure drops from 25 to, say, 20. And so now you have 15 pushing out, and you have maybe 2 or 3 pushing back in at the venual end. So one of the first symptoms you see in liver disease is edema. You see swelling everywhere because you can't pull the liquid out of the interstitial fluid back into the capillaries.